In real electrical systems, circuits rarely jump instantly from one state to another. When a switch is turned on or off, the circuit goes through a temporary period of change before reaching steady state. In this lesson, we will learn transient response and how circuits evolve over time after sudden changes in input. Transient response describes how a circuit behaves immediately after a sudden change in input, such as turning on a switch, applying a voltage step, or disconnecting a source. During this period, the circuit is not in steady state, and voltages and currents change dynamically over time until equilibrium is reached. This behavior occurs because energy storage elements like capacitors and inductors cannot change their state instantaneously. Capacitors resist sudden changes in voltage, while inductors resist sudden changes in current. As a result, the system must transition gradually from one condition to another. Transient analysis is one of the most important concepts in circuit theory because it describes real-world behavior. Almost every practical electronic system experiences transient effects whenever power is applied, removed, or modified. The transient response of a circuit is primarily determined by capacitors and inductors, which store energy in electric and magnetic fields. These elements introduce memory into the system, meaning the current state depends not only on the present input, but also on past energy conditions. In RC circuits, the capacitor controls how quickly voltage changes, while in RL circuits, the inductor controls how quickly current changes. In RLC circuits, both effects interact, creating more complex transient behavior that may include oscillations or damping, depending on system parameters. The resistor plays a different role by dissipating energy as heat, which gradually reduces the system's stored energy. This energy loss determines how quickly the transient response decays and how fast the system reaches steady state. Most transient responses in basic circuits follow an exponential function. This is because the rate of change in voltage or current is proportional to the difference between the current state and the final steady-state value. This leads to a predictable curve where changes are fastest at the beginning and gradually slow down as the system approaches equilibrium. The shape of this response is governed by time constants, which depend on resistance, capacitance, and inductance depending on the circuit type. Understanding exponential behavior is essential because it allows engineers to predict how fast a system responds, how long it takes to stabilize, and how it behaves under switching conditions. Transient response analysis is critical in almost every area of electrical engineering. In power systems, it helps engineers understand what happens when devices are switched on or off. In digital systems, it determines signal integrity during fast switching operations. In analog circuit design, transient behavior affects timing circuits, filters, and waveform shaping networks. Engineers must carefully design circuits to ensure that transient effects do not cause instability or unwanted signal distortion. Simulation tools rely heavily on transient analysis to predict real-world circuit behavior before physical implementation. This makes transient response a core skill for both theoretical understanding and practical engineering design. In RF engineering, transient response is critical for understanding how circuits react to sudden signal changes, such as pulsed signals or switching events in communication systems. Although RF systems often operate in steady-state sinusoidal conditions, transient effects still appear during modulation, switching, and signal startup phases. These effects can influence spectral purity, signal distortion, and system stability. Understanding transient response helps RF engineers design systems that minimize unwanted artifacts during signal transitions and ensure stable operation across varying conditions. In this lesson, we learned that transient response describes how circuits evolve over time after sudden changes in input. It is governed by energy storage elements and exponential behavior, and it determines how quickly a system reaches steady state. In the next lesson, we will compare steady-state versus transient behavior to clearly distinguish long-term and short-term circuit responses. If you found this useful, like the video, subscribe, and follow for the next lesson.